Hello everyone, and welcome back to On the Spot STEM. Today we will be covering 2017 Aime I problem number 12. This problem reads, call a set S product free if there do not exist ABC inside S, not necessarily distinct, such that A times B is equal to C. For example, the empty set and the set 16, 20 are product free, whereas the sets 4, 16 and 2, 8, 16 are non-product free. Find the number of product free subsets of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I think you can inherently see that this problem will involve casework, but we have to find a smart way to divvy up that casework so that we don't have to go through all 2 to the 10 subsets of this set. So how do you do that? Well, this condition is very nice because if you have a set where the smallest element is like A1 and the biggest element is A of k, if A of 1 squared is greater than A of k, then for every element between this, we can either choose it or we could not, because we know that the smallest value of A times B is always going to be greater than A of 1 squared. It's always going to be greater than the smallest value squared, because obviously that's what we want to do if we want to generate the smallest possible value. So if this smallest value is already greater than the largest value in our set, then for anything in between, we have 2 choices to either include it or not include it. So we can use this fact in divvying up our casework over here. And so what we notice is if 4 squared is greater than 10, since 4 squared is greater than 10, if we don't have 1, 2, 3 in here, and our smallest element is greater than or equal to 4, then we don't have to worry about this anymore, since A times B will always be greater than 10 for sure. So we can do cases on the smallest element using this. So if 10 is the smallest element, there's obviously 1 since you can't get anything else. If 9 is the smallest element, you can either choose 10 or you can not. So that's 2 choices here. For 8, the smallest element, you can either choose 9 or you could not, and same with 10, so that's 4. For 7, you have 8 choices since you can choose or not choose 8, and then 9, 10. And then for 6, you have 16 choices, 5, 32 choices, and 4 is 64 choices. And so summing this up, we get 127 choices right over here, if none of 1, 2, and 3 are inside the subset. So now let's add the number of times when 1, 2, or 3, or any combination of them appear in this. So let's do, going with our smallest value casework, if 3 is the smallest element in our set, then we have 4, 5, 6, 7, 8. We cannot choose 9 for sure because 3 squared is equal to 9, so that won't work, and 10. And now observe that for whatever other value we choose as the second smallest element, 3 times that second smallest element is always going to be greater than 10 since this is greater than or equal to 4. So since that is true, we don't have to worry about that, and we don't have to worry about our condition anymore. And so we essentially have 2 choices for each of these 6 elements. So that's another 2 to the 6 possibilities right here, and we can add 64. So now let's do the case where 2 is the smallest element, and now we have 3. If 2 is already in the smallest element, we cannot put 4 since 2 squared is 4. We have 5, 6, 7, 8, 9, and 10. Now we just have to do some casework on what we choose next. Let's going with the smallest element idea, let's let 3 be the second smallest element. If we choose 3 in here, then we cannot put 6, we cannot put 9. We can put 7, we can put 8. We have 2 choices for each of those. And if we put a 5, since 2 times 5 is 10, we can't put a 10. If we put a 10, then we cannot put a 5, since 2 times 5 is 10, and that would violate it. Or we could choose neither. So we have 3 possibilities for this. Because the only possibility where it wouldn't work is when both the 5 and 10 are inside the subset. So we have essentially 2 squared times 3 possibilities over here, which is 12. And now let's suppose we don't include 3. So if we don't include 3, what happens? Well, since we're not including 3, we can put 6, we can put 9, we can put 7, we can put 8, or we could not put them. There are 2 choices for each of these. And this is because 2 times 6 is greater than 12, greater than 10, so it doesn't really matter whether we put it or not. And again, we cannot put both the 5 and 10, since 2 is already inside of here, so that's another 3 possibilities. So it's 3 times 2 to the 4, in this case, which is equal to 48. And adding this up, we have 60 subsets in the event that 2 is the smallest element. Now let's do, we can add 60 here, and now let's do the cases when 1 is the smallest element. This is a really easy case because 1 squared is equal to 1. If we put 1 as a subset, then we already have the restriction that AB equals C violated, and so we cannot do that at all. So we just add a plus 0 to our count over here. And we cannot forget the empty set, of course, so we add 1, because in all of these cases, when we did cases on the smallest element, we guaranteed that the size of the set was at least 1. So we have to take the case where the size of the set is 0. And this is all. We did casework on everything using this method. And we know that we did casework on everything because we consider the case where every single element is the smallest in its subset. And so the sum of this is equal to 191 plus 60 plus 1, which is equal to 252. So 252 is our answer. We can mark this and move on, and we are done. And to recap, what we did was we knew that we had to do casework on this set, and so we noticed the restriction was nice for when A and B are when the smallest elements are relatively large in comparison to the largest element. Essentially, when the smallest element squared is greater than the largest element, then we don't have any other worries because the smallest element squared, since it's greater than the largest element, then any other two elements, when you take their product, will be greater than another element of the subset. So we extended that idea to doing casework on the lowest element of the set, and if we do casework on the lowest element of the set, and we cover all the elements in our set, 1 through 10, then we know we've exhausted everything, and we've done that, we got our count, we got 252, and we are done. Thank you for watching. If you enjoyed this video, please like and subscribe, and please tell your friends about this if you haven't already. And if you want any other problems to be done, just you can send us an email at onthespotstem@gmail.com, or you can leave a comment down below, and we will try to get that. Also, if you have a Facebook, then go like our Facebook page. You can just search up On The Spot STEM on Facebook, and it will lead you to our page. Thank you.